Good morning, everyone. Welcome to Autodesk Virtual Academy. I'm Nigel Mbayak, one of the customer success managers here at KETIV. Today, I'm joined by one of my good friends, Alex Alvarez. Looks like Alvarez is actually in the office today. Good morning, Alex. How's it going?
Good morning, Nigel. Pretty good. Not too bad.
Awesome. Good to hear. Good to see. So I know that we've been talking about doing this for quite a long time, Inventor tolerance and stack-up analysis within Inventor. This is something that's included within the product design and manufacturing collection. Definitely wanted to make sure that everybody's aware that likely you already have access to some of these tools and you can use them at any time. So Alex, do you have anything else to add before we go ahead and get started here?
No, I think we're here for a pretty good session. So hopefully you guys are able to pick up a thing or two. This is something that, like you said, right? It's been requested quite some times now. So hopefully people who requested it are on the line. Again, if you guys have any questions, don't hesitate to ask. We'll do our best to either answer them throughout the webinar or at the very end.
So without further ado, I'll go ahead and pass it off to my good friend Alex here. Alex can go ahead and get started. We'll be here for the next 30 to 40 minutes or so. And so enjoy, everybody. Alex, take it away.
Awesome. Yeah, thanks for that, Nigel. All right, guys. So again, not really learning objectives here, but these are key things that I want you guys to keep in mind. Like I mentioned, I've had numerous discussions with customers where we begin talking about their tolerance analysis. Again, we start off with talking about the design workflows, how they're handling the design and manufacturing process. As soon as we start getting into tolerance, they stop me right away, right? Hey, that's not our issue. And again, for the most part, I'm talking to designers and engineers, but they usually tell me, or for the most part, they're telling me that's going to be on the manufacturing side. Manufacturing handles all of the tolerancing. Now, again, nothing wrong with that, but what they don't understand and what they don't realize is that manufacturing has to go back to engineering 4, 5, 6 different times even throughout the day, trying to clear up some of these ambiguities, right? So trying to make sure that they're both on the same page. So again, there's a lack of efficiency there. There is going to be some time wasted. So what I want you guys to keep in mind throughout this webinar is how can we use Inventor tolerance analysis to communicate these analysis results with manufacturing and quality much more seamlessly, right? So again, if you're one of those people that is currently letting manufacturing handle that, no problem. Like I said, there is some inefficiencies there. Maybe you're not even taking care of or not analyzing tolerance. You might have some bigger problems if you're not currently doing that, right? So if again, if that's something that you're currently doing, that's something that we can help you out with as well. So like Nigel mentioned, the tolerance analysis is actually going to be built into the product design manufacturing collection, right? So it is a part of the collection. You guys wouldn't believe how many times we get calls asking for pricing around just the tolerance analysis add-in. It is built into the tool. So if you guys need help locating where that's at, maybe you guys need help getting access to the tolerance analysis add-in, give us a call. We're going to be here to help you guys out, right? So again, make sure that if you do have the product design and manufacturing collection, be aware that you do have you have access to this tool currently. All right, so why do we even need to consider tolerance stackup in the first place? So as many of you know, dimensional variation can have a pretty drastic impact on your product. Just a few things that can cause that: tool wear, right? It not only leads to quality issues, but it can also affect the final size of our product. If you're working with some sort of tool holding, maybe you have the part on a fixture, there can be slight deflection. Maybe the tool is, like I said, a little worn out. There's going to be a little bit of deflection on the tool as well. And what that's going to lead is to inaccurate dimensional tolerances, right? So that's why you have to start looking at what the tolerances are. In the perfect world, every single manufacturing shop would hit the value that the part was designed to. Again, we don't live in that perfect world, right? So there has to be some deviance, there has to be some tolerances allowed in those different dimensions. If you're working on a part that is going to be put under a lot of stress, maybe it's going to go through thermal expansion, kind of like you see that with that rotor, it's going to expand a little bit, right? Did you account for that tolerance? So again, there has to be tolerances that have to be incorporated into the designs. Otherwise, you are going to run into some pretty major issues down the line, or even worse once it actually gets released. You can have a lot of warranty issues. So these are all things that we need to consider. Again, precision goals can be met several ways, especially with manufacturing. if you're gonna grind a part, maybe you really want to make sure that you get the surface finish to a specific measurement. Maybe the tolerance also has to be a little tight there. That's gonna just drive up the cost. Is that really necessary, right? So what we're here to do today is to really analyze where can we analyze some of the trade-offs. Where can we maybe make the tolerance a little bit more coarse? Where do we need to tighten it up? And again, Inventor tolerance analysis, for those of you that aren't aware, it is fully integrated inside of Inventor. So ultimately, like I said, our goal is going to be to optimize these tolerances to create a cost-effective design for manufacturing. And this is where Inventor tolerance analysis shines, because again, not only is this tool analyzing the different tolerances of your assembly, but it's also going to be built into the software that your designers are currently using. So there isn't going to be a steep learning curve. They don't need to relearn a brand new tool. It's going to be a interface that they're completely comfortable with and they're already accustomed to using. So again, this tool is going to enable users to really increase the understanding of the part function early in the design phase. Right? So again, typically in a design cycle, you're going to create these designs, but then towards the end, maybe you miss a step, maybe you're not sure how these components are going to be put together, maybe you underestimated a specific component or the tolerance for a specific component. This is going to get you to really understand and dig deep into how a tolerance affects the overall assembly. So let's go ahead and take a look at just a very simple example. Again, we're going to start off with this, essentially there's just 3 components here. If you take a look at the first image, right, so that's the scenario where if the parts were all manufactured to nominal dimensions, that's what we're aiming for. Right? So we're aiming for, and this is metric, so it's going to be 0.5 millimeters. Now, what happens if we manufacture the entire parts to the minimum material condition, right? So the least material condition scenario would give us a 2 millimeter gap. Now, is that okay? Is that something that we will be comfortable releasing to the product or to the market? That's going to be up to you guys. So what I do want to make sure that you guys are aware of is you still have to understand how this product is going to function, right? So again, if that 2 millimeter gap is okay, then by all means you can release that product. If not, then you need to make sure that you tighten your tolerances a little bit. Now, what happens if we machine or manufacture these parts to the maximum material condition? Right, at the maximum material condition currently, as it sits, it would have a 1 millimeter interference. Now, again, 1 millimeter is equivalent to 40 thousandths roughly. That wouldn't fly with us, especially considering the material type. Maybe it's a plastic part. Maybe it's, depending on what the components are made of, maybe there's some sort of give there. But if these parts are steel or some sort of other material, that 1 millimeter interference isn't going to fly. Right. So let's go ahead and take a look at this example here inside of Inventor, just to get a quick understanding of what the tool looks like, and then we'll jump into a little bit more complicated one. Okay, so like I mentioned, we're going to be inside of Inventor. Once you download the add-in, again, if you have the product design and manufacturing collection, you already have access to this tool. You do need to download that tool though. So once you download it, you are going to see it inside of your environments tab. Right? And again, notice that I'm in assembly. You can analyze parts if you wish, but again, it makes the most sense when you do a tolerance stack-up analysis on an assembly, right? So for this one, we're going to go ahead and just select tolerance analysis, and we're going to be presented with this dialog. So again, it's going to say that it's a 1D tolerance stack-up. Not to get confused, a lot of people think that 1D means that it has to be on a 0 degree angle essentially. But if these parts, if you could think of it, if they were at an angle, slanted, and you had these components lined up on that slot at an angle, that's still considered 1D, right? So what we're analyzing is a 1D loop. So the mates, so we have a couple constraints here. We have a flush constraint, or just a constraint with one face to the next. We're going to have another flush constraint here, and then so on and so forth, right? So again, that's essentially just a 1D loop. What this means, so 1D, 2D, 3D, starts talking about whether you have additional components here. So we'll talk a little bit about what 1D versus 2D versus 3D tolerance stackups mean, and hopefully that can clear up a few of the questions here. But anyway, so for this one, what are we trying to analyze? Right. So which is the gap that we're trying to analyze? Like I said, there's going to be a 0.5 millimeter gap in between this component and this face. Let's go ahead and create a new stack up to analyze that, see how the tolerance is affected. Right, so we have a new stack up created. We're going to go ahead and analyze the face there and this face here. Pretty straightforward. The software actually walks you through exactly what's next. So you can see that the annotation plane, where do you want to place these annotations, pops up. We can go ahead and select that plane there. Now, this is pretty important, right? Because again, it's pulling and it's extracting all of the different constraints that you guys are creating inside of Inventor. So again, you don't have to do any of the rework. Now, this is a pretty big deal because even if this was an imported part, let's say we had an assembly that didn't really have constraints, maybe we imported it from a different CAD software, that's okay. You can manually set these constraints. So you don't need to have constraints in order to get this to work, right? But again, if you do have constraints, it just makes things a little bit easier. So it found one path. We're going to go ahead and select this mate 2. Again, why are we interested in these constraints here? Because again, that gap, depending on what that gap is or what the component size of the tolerance for these components is going to affect the spacing in this entire slot. Right? So again, if we have maybe a small tolerance or a tight tolerance for these, you're going to have a bigger gap. That's going to affect the overall slot, right? So we're essentially analyzing the loop between this face right here, this face, and then this face pushing up against this opposite face of the actual block, right? So that's why it's important to really understand which loop we're going to be analyzing. So for this one, we're going to go ahead and select the set of constraints there. We're going to go ahead and hit the green check mark, and then we have the stack of details, right? So a lot going on here. I'm going to break it down just so you guys can see what's going on. I'm going to clear some of these values just so that we can start fresh. So it pulled in all of the different components that we have. It also pulls in the dimensions, right? So notice that you can tell that it actually pulled in the nominal dimensions here. And what's nice about this, and I didn't add any GD&T on purpose to this model just so we can see the difference, but you can actually specify what the tolerance is inside of here. Now you'll see the little link icon right next to it. That's indicating to you that whatever change you make to the tolerance here is actually going to affect the model, the model IPT file, right? So you do have the option if maybe you're just trying to do a quick compare, just to see if a specific tolerance is going to affect it drastically or not. You can click on the check marks on the little chain box, and it's going to break the link, right? So you are no longer affecting that model, or you're not going to be able to update that model. Right, so that tolerance isn't going to affect it in this case. But again, if we're trying to really analyze and make sure that these tolerance backups are going down to manufacturing, you want to make sure that these updates do take place. So for this one, I'm going to go ahead and say 0.5. You'll see that the stack up here, right? So the gap that it found is going to be 0.5. You'll see that right now the tolerance for that single part, so that's the only part that has some sort of tolerance, is also set to 0.5, right? So we're in the clear, and that makes sense because again, the gap that we have is going to be 0.5. We have a tolerance on a single part that's 0.5. Therefore, we can either be at the max, so we can be at the flush condition, or we can have that gap of 0.5, right? So we're still going to be in the green, but as soon as we start adding tolerance, obviously we can have a tolerance of 0 here. Let's say we start increasing the tolerance there. Maybe you want to increase it to this one as well, right? And in real time, you start seeing this graph down here update. Now it found that the total tolerance backup is going to be -1, right? And so what this is indicating is that you have a upper limit of 2, lower limit of 1. Some of the parts are going to be in the green, right? So some of the parts are actually going to be okay to actually assemble and be able to fit inside of this slot. But there are going to be a handful of parts that don't fall and don't meet that criteria, right? So now you can quickly start seeing what tolerances make sense. Where can you apply some of the give? Where can you be a little bit more tight on these tolerances? And then in here, a little hard to see. Now, typically when I'm working with this tolerance analysis stackup, I do like to bring this you can move it, right? So this is, you can undock it. You can bring it back if you wish. So when you're doing the tolerance stackup, it's sometimes a lot easier to just move it to a separate window, right? It makes it a little bit easier to work with it. So again, we have 20, plus or minus 0.5, 30 plus or minus 0.5, you can tell that that's not going to fall within our range, right? So maybe we want to set an objective here of symmetric, right? So we want the gap to be 0.5, but again, we can give it a little bit of tolerance. We can say we want a plus or minus 0.25 tolerance on that gap. And again, it updates. You can now clearly see that we're definitely not going to meet the specifications there. There's going to be a large range of parts that don't meet that criteria. So again, what I can do is say, okay, well, maybe I want this to be 0.2. Maybe this bottom tolerance is 0.1. Do the same thing for this bottom component. Right, so again, update the graph in real time, but you can still clearly see that some of the parts that we manufacture are not going to meet that specification. Now, this is where you have to be careful, because what we're analyzing right now is actually the worst case scenario, right? So it's taking a look at the maximum material condition parts. So it's assuming that every single time you're going to select the maximum material parts or the minimum material parts, right? And it's going to give you a graph based on that assumption. So that's what worst case scenario is doing in this case. Now, hypothetically speaking, that isn't going to happen, right? So when you're manufacturing these parts, some of them are going to hit that upper limit, some of them are going to hit the lower limit, but the chances of you selecting 2 or 3 components that all represent the maximum material condition are going to be very, very slim, right? So instead of doing a worst case scenario in this case, what we can do is we can hit the drop down. We do have a few options here to select from. I'll get a little bit more into the statistical analysis here, but let's do an RSS. Let's do a root sum square. Changing it to an RSS study actually indicates now that majority of our parts are going to be met or they're going to be manufactured to the nominal dimension, and you can tell by using by what this graph is representing. Right, majority of the parts here are going to be manufactured to the nominal. Again, this is using statistics. There's going to be a few parts that are going to be right here on the high side, a few parts over here on the low side, but we're still going to stay within that range that we're looking for, right? So that 0.25 plus or minus 0.25 range that we specified. Again, if you want to go ahead and export a report from this, you can go ahead and do so. We'll actually export a report here on this next example. But you do have those options here as well. You can take snapshots, show the snapshot, manage settings. So you can tell that as soon as I launched tolerance analysis, there was actually some pre-default settings here that you can manipulate. You can go to the manage settings panel. And depending on which units you're working with, you can specify some of those settings, right? Do you want the default target quality to be worst case, root sum square, statistical? If you are working with statistical, which process do you want to select? Right, so process capability, so using some sort of a quality correction factor. These are values that you can actually get from your supply chain. So your supply chain, if you're doing some sort of manufacturing in-house currently, you can get these values and make sure that you get actual realistic statistical data off of this, right? So DPMO, defects per million, you can do the same thing here. Percent yield is very similar to defects per million. It's just a percentage of that, or it's represented as a percentage. So again, you have a lot of different types that you can run. But again, I want you guys to just be careful with the worst case, because again, worst case is assuming that every single time you're going to be selecting the worst case parts to assemble. And so sometimes it does give you a false preview there. And that's really going to be it, right? So again, it gives you the opportunity to not only finish your design, and it doesn't even have to be a complete design here. Maybe you're analyzing a subassembly, right? So you're analyzing a subassembly, take an hour, 2 hours, run the tolerance analysis, and then see if you're designing or if your design is going to meet the correct specifications there. And so let's go to a little bit more complicated example and see what that would look like. Again, we have a gear reducer. We have a few view representations here that we can select from. So I'm going to select the slow speed shaft representation. Same exact thing we did with the simple analysis. We're going to go into our environment tab, select tolerance analysis, right? And now we can go ahead and create a new stackup for this. So we're going to select new stackup. What do we want to analyze? Well, we want to analyze the spacer here and then how is it going to be affected if we increase the tolerance, or if we have some tight tolerances, or how coarse can we get on the tolerance, right? So again, if the tighter tolerances that you add to these components, the higher it's going to drive up the manufacturing cost. You're going to have to spend a lot more time trying to hit those specifications, hit those tight tolerances. So again, it's just going to hike up the manufacturing cost there. Which, by the way, let me go ahead and just finish analysis here real quick. We actually have GD&T on that spacer. So if I take a look at the slow speed spacer, we actually did a webinar on this as well on model-based definitions. So again, if that's something that you're interested in, just go to our YouTube channel, search up KETIV model-based definitions, and this should be one of the videos that pops up. But what's nice about this is that, again, these model-based definitions, they're not only being populated into your drawings, but the tolerance analysis is actually extracting that information as well. All right, so again, if we go back to our environments and select tolerance analysis, create a new stack up, let's go ahead and analyze now that gap. All right, so again, you can go ahead and select the gap there, and then select the space here. Same exact workflow, right? What's the annotation plane? I'm going to go ahead and select this YZ plane. And now you can start seeing that it's doing the same exact thing, right? So again, it's going to analyze that gap, and let's go ahead and just place that dimension there. Same exact workflow is going to say that it found that path. And again, the path that it found is that spacer. That spacer is going to push up on this component here. That's going to push up on the gear housing, and then it's going to repeat on the opposite end. Right, so we want to analyze that 1D loop. We want to analyze how these components are interacting with one another and how the tolerances are going to be affecting each component here. So we're going to go ahead and select that. Again, it gives you a nice little preview of the different constraints. Right, so you can quickly see, make sure that you do have the correct constraints selected here. We'll select that one. Hit the green check mark, and then we get all the information extracted, right? So now we have a little bit more information here on the right-hand side. So I'm going to make this a little bit larger just so we can see. But notice that now we have the actual GD&T information, or the model-based definitions that we created, extracted from those models. So again, we don't have to recreate any of this. It's automatically extracting all of the tolerancing that we added to those components. Now, there's a lot more going on now, and again, this is more or less somewhat of a simpler example. But imagine if you had a decent amount of components that you had to analyze. How do you know which one is contributing more to these results at the very bottom? How do you know which component is contributing to the stack up? You actually have a contributions option here. So if you click on contributions, it gives you a pretty good graphics here indicating to you which components are contributing the most to the stack up. Now, it makes sense if you really look at it. The slow speed spacer has a tolerance of 0.5, whereas the rest of the components here have a tolerance of 0.1. The gear housing, same exact thing. If you take a look up here, has a tolerance of 0.5 as well. Right, so let's go ahead and take a look at what these tolerance changes can do for us. Right, so again, we'll take a look at the gear housing first. It's set to 0.5, so we'll go ahead and set this to be, let's say, 0.2. Again, it starts updating this. You want to make sure you set your objectives beforehand, right? So again, it's set to the gap be greater than, in this case, 0.28. But what we can do is we can actually set an upper limit, right? So we're going to set an upper limit there. Now, what do I mean by that? So the upper limit can be 25,000 or 0.25, sorry. Right, so why am I setting the upper limit to be 0.25? Well, let's assume that the material that these spacers are going to be manufactured or made out of is going to be something that can be compressed, right? So there can be a 0.25 interference between the spacer here and then the actual component that we're going to be using, right? So the upper limit is going to be 0.25. That's the max that I want that space or that compression to be. Again, you can see that the total tolerance stack up right now is set to 1.08. So let's go ahead and start making sure that we change some of these options as well, right? So we have the gear housing, we changed that to be 0.2. It was at 0.5. You want to be careful here because, again, you don't just want to look at the graph and start getting crazy with the tolerances. right? So our main goal is to not only give the tolerances the coarsest value possible, but we also want to make sure that these components all fit together at the end of the day, right? So again, the gear housing is 0.2, again, is set to be 0.5. The spacer here is also pretty coarse. You can see that there's two spacers, they're 0.5 each. I'm going to set this one to be 0.1. Same exact thing that we did with the basic component, right? So it gives us that graph. Again, it's telling us that there's still going to be some components here that are manufactured that aren't going to meet that specification. But again, take a look at what we have. So we're still in the worst case scenario. So if we switch back to RSS, again, now you can start seeing, okay, maybe there's going to be just a handful of components here that don't meet that specification. Right, so what can we do here? Again, you can go back into the tolerances. You can see, maybe there's a component in here that I can probably change, get the tolerances a little bit tighter. That's something that you can go ahead and decide. But again, if this is okay for you and you're okay with these tolerances, again, looking at the graph, you want to make sure that this actually meets the criteria. Right, so again, 0.25. We can come back here. Let's see, the gear housing, that's 0.2. Low speed spacer sets 0.1. For this one, let's say I'm going to be okay with that, right? Maybe you want to be a little bit tighter on low speed spacer, right? Again, increase a little bit, kind of hard to tell, but it does increase, it does change. You can take a look at some of the other studies that we have here. So RSF, let's go change the statistical and then go to BTMO. Again, majority of the components that we create are going to fall within specification or within range, within tolerance, but there are going to be just a slight handful of components that don't meet this criteria, right? And again, if you're creating a one-off, maybe this isn't something you're really looking at, right? So maybe this isn't as important, but once you start doing a production run, you really start looking at how many components are meeting the tolerance specification, how many are falling out of range, how many outliers do you have. This is information that's going to matter to you guys, right? So for something like this, again, if you're happy with the results, what you can do is now we can go take a snapshot of this, because now you want to start sharing this information with manufacturing, right? Maybe running the numbers, making sure that these numbers make sense. Go ahead and take a snapshot, generate report, and then specify where you want this report to go, right? So we'll say slow speed. Now, what's nice about this report is that it's actually an HTML. So you can send this out to someone on the shop floor. Maybe they have, they have an iPad, maybe they pull this up on their iPhone, and they can see exactly what's going on here. Now, if I export this out, you can see that it didn't meet that criteria. It didn't meet that specification that I was aiming for. Right, the objective was 0.25. You have a nominal of 0.03 deviation there. Number of dimensions that it pulled out, and it gives you that cross-sectional view. So it's pulling out all these images, and it's pulling out all these dimensions for you guys to both take a look at. Right, gives you a pretty nice updated report here that you guys can start analyzing. So you can see it does give you a indication here that there are going to be a handful of components that don't meet that range. Right, so maybe you need to take a look at some of the dimensions or take a look at some of the tolerancing that we specified and seeing where do we need to tighten up some of those tolerances. And again, it shows you the contributions for which component is actually affecting that tolerance stack up the most. Right, so again, this is a tool that I envision a lot of designers, a lot of engineers using in the very beginning of the design process. It just allows them to really understand the form, fit, and function of the components, and allows them to quickly see if a tolerance makes sense or if this is a conversation that they need to have with manufacturing a little bit more, right? Instead of tossing this to manufacturing, letting them create the tolerancing for it, and then creating a prototype, and then realizing that, you know what, maybe the tolerances were a little bit off. So what do? Tighten up the tolerances, create another prototype, but again, that's going to be time wasted, and that's going to be an actual material that gets scrapped. Right, so take a look at this tool. Again, very easy to use. If you guys have the product design and manufacturing collection, this is something that you guys can use today. So if you guys have any questions on this, this is probably a good time to take a look at some of the questions that were asked. Maybe you guys want us to go through one of your examples, right? Give us a call as well, and we can go ahead and analyze kind of what you guys have currently. But Nigel, did we get any questions come through? I'm not sure if.
Yeah, there's a couple that have come through. Will this also work with angular dimensioning or just linear dimensioning?
So as of right now, it's just going to be linear dimension. And one thing, actually, let me go back to one of these examples here. Right, so let's take a look at the 3D effects detected in the stack-up analysis. Again, reason why this comes up, or why this indication or this little warning comes up, is because if you take a look down here, we have a dimension of 50.5, right? And that's fine, but what happens if there's a little bit of taper on this wall, right? So we're still going to get 50.5 here at the bottom, but now our tolerances are completely thrown off because there's a slight taper on this wall. So there's no GD&T applied to the faces currently, right? So if we take a look at how this affects the analysis, it actually gives us a pretty good indication here of the difference between 1D and 3D. So you can kind of see, right, if you have, this is a caster and this is a Autodesk example here that we use quite often. But if you take a look here, it's no longer necessarily a 1D example. You still can analyze this, that's no problem. But Inventor is actually going to throw up a warning saying, hey, this has some possible effects, so this has some side effects here, because again, if you don't have this correctly manufactured, so there is going to be a slight rotation. If the holes here are maybe angled or slightly offset, there's going to be a slight offset, and what that's going to cause is it's going to cause pinching on your tolerance, right? So this is something that currently at the moment we can't analyze because again, this turns more into a 3D tolerance analysis instead of a 1D linear tolerance analysis. So you do want to be careful with components of this kind. Again, if you guys want to learn a little bit more, there's actually some pretty good examples. If you go to the Home tab and if you go to the tutorial gallery, I want to say I've seen 1 or 2 tutorials here that actually walk you through tolerance analysis. So if I take a look here, so define a tolerance backup, I think that's one of them. I want to say that there's probably another one that walks you through. But again, very easy tool. Like I said, most of what I covered today is going to apply to majority of the assemblies that we've worked with in the past. And again, just it gives you a nice visual representation of how your tolerances affect your entire assembly.
And Kevin asked,
so good question. Hopefully answer that.
Yeah, hopefully too, Alex. Kevin asked a question: how does temperature fit into the analysis? So I don't believe that's taking any of that into account for this. If you're looking at how temperature is going to affect how your assembly is built, there are other solutions for that aren't necessarily just Inventor tolerance analysis. You probably have to fit some analysis, some simulation in there as well, whether that be like fun stuff like that.
And that's what I was. Yeah, and that's exactly what I was going to say, Nigel. Is you can use Nastran NCAD, right, or even the stress tool that's built into Inventor. Analyze the thermal expansion, and what you can do there is you can see what the increase in size is going to be, right? So maybe it's going to increase if it gets heated up. Maybe there's a 1 or 2 thousand increase in a specific dimension or in a specific length or width. You can now bring in that information again with running the study analysis, but now you're going to know, okay, I need to account for this 2, 3, 4 thousandths of an inch due to thermal expansion. So now with that information, now you can come in here to tolerance analysis and then account for that expansion.
Yep, it's just a 2-part thing.
Yeah, tolerance analysis wouldn't specifically do that for you.
Yeah, and if you want to know more about that, if that's something that kind of interests more people, let us know and we can see if we can put that workflow together right, is understand what this is going to look like from the actual simulation side in terms of applying those thermal loads onto your components, and then using that information, right, to come into the tolerance analysis and make that even more powerful, right, like it even more real world in terms of what it's going to look like.
Yeah, absolutely.
There's a couple of questions. There's a couple of people who are like saying that they want to comment their issues in some of the post-webinar surveys. Awesome. So yeah, if you have more personal, in-depth things you want to take a look at, that's what we're here for. So reach out to us. You can even email Alex. Don't email me, just email Alex. I'm just kidding. You can email either of us, and we'll make sure that that gets answered from either way. And there's a couple of people asking for recordings of this webinar. So it'll be up on our YouTube channel shortly. So if you just Google, not Google, if you go onto YouTube and you search Inventor tolerance stack-up analysis, you will find this video, or just look at our YouTube channel and we'll have it there as well.
Perfect. Yeah, there is one last thing, Nigel, I wanted to bring up. Again, we've been promoting this for a couple of weeks now, but we do have the Advanced Manufacturing Summit. So Autodesk actually hosts a summit. Normally it's live, it's in person, but again, with everything going on, it's going to be more of a seminar type. So this is something that everyone can attend, and they're going to be talking about all of the different manufacturing tools. So anything from subtractive, additive, injection molding. If this is something that you guys are interested in, the registration is actually free. So you can sign up, talk to industry experts, get to connect with some of these people, and then get some of your questions answered. Like, it is going to be hosted by Autodesk. So if this is something that you guys are interested in, by all means, check it out. Right? And I believe it's happening next week, if I'm not mistaken.
Yep. And the link is there in the chat. So if anyone wants to go ahead and click that, you can go ahead and click that within the chat itself. And then a question from Philip. Can you review again how to specify the minimum and maximum gap or interference when entering the objective? Do you want to run through that?
Oh, yes. Yep, let me run through that. So if I go back to my tolerance, so this is the objective right here, right? So right now the gap that it identified is going to be 0.5. So you can either you want an upper limit, maybe you want a lower limit for that, right? So you want to stay more on the lower end of that tolerance. But for us, I want it to be a symmetric limit, right? So I can set whatever tolerance I want for that, and I set that to be 0.25, right? So what I'm saying here is that I want that gap to either be within 0.75 or 0.25. Right? So on the higher end, it's going to be 0.75. Lower end, the closest that I can get these two faces together is going to be a 0.25 millimeter gap. And again, that would just be something from just from experience, right? From your knowledge, coming from your experience with the actual product. That's kind of where this value came in from. But that's how I would set it. I just do a symmetric tolerance and then set the objective here to be 0.25.
That works, yeah, and there's kind of a graph down there at the bottom that shows you what it's going to look like if you add or subtract 0.25 millimeters, right, is you're going to get to either 0.75 or 0.25, depending on which direction you go from that value. All right, question from Kelly. Would changing the nominal size be the same effect if the tolerances were left as originally started? Can this be changed through the analysis also?
Oh, so you're asking if you can change the nominal. So again, nice thing about working with this tool is that it's completely built into the software. So if you do change the nominal size, it is going to update your results here. Typically speaking, if I were to manufacture a part, I'm always going to aim for the nominal, right? So again, I'm always aiming for that value that we're setting. Obviously, the tolerances are there just to kind of cover me, make sure that I actually have some sort of deviation from that. But if you change your nominal, then again, most manufacturers are going to hit that nominal. So again, depending on how your manufacturer likes to work, I would honestly say just give them a nominal value to whatever you want to set that part dimension to, and then give them a tolerance that they can stay within. But you can change the nominal, and it would affect the results here inside the tolerance analysis. The only thing is that you can't change them inside of this box. You would have to open up the part and then change them there.
Yep, and I just want to reiterate too that Alex has not left Inventor this whole time. Well, except to go to PowerPoint, I guess. And this is all completely built into the software. And if you're a product design and manufacturing collection customer, which I would say 90% of the people on here are, you already have access to this. And like Alex mentioned at the beginning of the webinar, we always get questions like, how much does that module cost? It's like, well, you have it. So if you have any questions about what's included within the software that you do have, definitely reach out to us and we can go ahead and take a look at that for you as well. So, and then this is a great question from Claudio. When you set the tolerance in the advisor, does that information carry over and then pull those tolerances on the drawing side of things?
Absolutely. Yep. So if I take a look at this dimension here, let me change this to 0.1. Oops, not plus 1, 0.1. Kind of hard to see here, but you can see that it's now 20 plus or minus 0.1. So that information does carry over to your model, and it does carry over to your drawings as well. Again, granted that you have the actual link here turned on. If you have that turned off and you just want to experiment with some of these values, that's completely fine. You can do that as well. But now it's no longer going to affect your model here. Still going to create the tolerance for you, but it's not going to change the actual model values.
Yep, it's the same thing of being associated with the drawing views and the model, right? Mm-hmm. It's the same concept that they're using here. So, and Alex, if I remember correctly, those annotations won't show up in the drawing unless you turn them on, right?
You have to turn them on, yeah. So these are just annotations or 3D annotations, but yeah, you would have to turn them on inside of the drawing.
Yep.
And again, one of the nice things is that, again, so for the slow speed spacer that we have here, we can extract all of the model-based definitions and add them to our drawing, right? So now you have a single source of truth coming from this model. And again, if you change any tolerance or any geometric tolerance here, you can actually see that populate too in the drawing as well.
Yep. And
so you can extract this information.
Yeah, and if you want to get really fancy and you don't want a two-dimensional drawing, you can export a 3D PDF. That's something we've gone over in the past too, and that'll have all of the model-based definition on it as well. So if you want to get real fancy, you want to give someone a 3D version of your file that's in like PDF form where they can't like open it and edit it, all that fun stuff. But you want these dimensions and these all of these other definitions to show up, the GD&T stuff. You can just export a 3D PDF and boom, you got it. So.
Yeah, and that can even be a topic that we discuss later, right? Is how do you export to a step 242 and then get this out to quality? I know there's a lot of CMM softwares out there that actually run off of a step 242 file, and they'll actually bring in this information that you can extract all of this without having to recreate this in the third-party CMM software. So pretty awesome stuff actually that you can do.
Yeah, that's where Alex lost me. That's where Alex's expertise in the machining world definitely goes above and beyond my head. So if you're interested in that, whatever Alex just said, I'm just kidding. I kind of got the gist of it. Definitely let us know, right? And we said earlier that the inventor tolerance analysis was something that a lot of people were asking us for, and so we made it happen. Likewise, if you all have something you want to see in the future, let us know. And we'll go ahead and try to make that happen in our schedule in the near future. So it is the people who are watching, the audience themselves, who help drive where we take these. So the more and more we hear of the want to learn something, the more likely it'll be on the calendar sooner. So definitely reach out to us if you want to see something specific. All right, I think that's it for questions, Alex. If anyone has anything, you have our contact information. Feel free to reach out to us. We're more than happy to answer any questions, have deeper dive conversations with you, and square this all away. But for now, go ahead and get started using some of these tools, right? You do have them, so might as well take advantage of them, right? Alex, anything else to add before we let everybody go?
It's going to be it for me. Have a great rest of the week, guys, and we'll see you on the next one.
Absolutely. Take it easy and stay safe, everyone. Bye-bye.